Okay, so yeah, so today I will go over like the midterm solutions. So I have the solution with me, and then I gonna maybe go over the solutions and try to explain like why the solution is like that. So maybe it's easier for you to study for the midterm. So for the first one problem is for millimeter wave phase array can be integrated into handheld device. Why is it difficult to integrate an RF phase array in handheld device? Okay, so for this one the answer is B, and the reason is like from the distance between the antenna elements is like λ/2, and like in millimeter wave, like the wavelength is smaller and smaller, and so it's how can I annotate? It's just like more compact form factors, and then it's easier to do millimeter wave on the small device compared to RF. Just trying to do annotation. Just okay, so the second question is basically like, it's comparing the inductors with ground and without the ground shield, and which one has like higher Q and lower and higher SRF. And so the answer is C. The inductors with the ground shield has higher Q and has lower SRF. And probably I'm gonna go over this one again. But basically you have like let's say you have like an inductor like this, and you have like ground shield, and so when you have port 1 here, and you have port 2 here, okay, and so if you let's say you have some signal at port 1, and for port 2 you ground, and so the current falling path gonna flow on inductors, but there's also like a return path for the current which flow on the ground. And so if this ground is good, is a good ground, then there's no like the path for the return current going to be good, and then this has lower resistance. But like if you have no no ground for no ground, for example, then the current have to flow through the substrate, and the substrate is normally has like is lossy, and so like it's gonna affect it increase the series resistance, and then it lower the Q of the inductors. So with the ground, you can have better Q, but you have like more like shunt capacitor, parasitic shunt capacitor, and so these capacitor make your Q your SRF lower. So that is for problem 2. Then problem 3. Phase invariant gain control is desirable in phase array, so that the solution is C. The phase array beam side node can be modified by matching the beam pointing direction without needing calibrations. So for this one, I haven't like reviewed the phase array material much. So maybe you guys can take a look at this and figure out why it is like that.
Oh, why A is not right?
I'm sorry.
Why A, the first one, a sink shaped beam can be formed in a broadside direction without needing calibration. That one is not right.
So I think. So I'm not sure about this question. I need to like review the phase array material. Yeah. Okay, so for problem 4, TXRX switch design using quarter wave transmission line. Identify which configuration correspond to which mode of operations. I correspond to TX mode of operations. Okay, so for this one is referring to figure 1, which is this figure, and So like we can start with this figure first. So you see like in here you have like an LNA for receiver path and a PA for the transmitter path, and you have like switch here, and you have for the wavelength transmission line. And so one properties of the transmission line is it can do of a quarter wavelength transmission line is that it can do impedance transformation. So let's say if you have some let's see you have like some z load at the one end of the transmission line, and this line have a length of lambda over 4 with characteristic impedance of z naught. Then if you look into the transmission line, what you see is z naught going to be equal to z in going to be equal to z naught square divided by zl. Okay. So in this case, in this figure 8, if we look at the like the transmitter path from the antenna, then we're gonna see infinite impedance. Is infinite because like you have like a short to ground at the load positions, and so like this one is like 0, and you have infinite here. And then like for the RX path is always like Z naught impedance because like it is impedance of the element. So and then the opposite is like is for the figure B, and in figure B, like if you look at the LNA path, you see like Z naught is infinite. And for if you look at just meeting path, then Z naught is Z is 50, or yeah, Z naught. And so so from this intuition, we can see that figure A is for receiving the signal, and figure B is for transmitting the signal. Okay. Let's see. Okay, so figure problem 5, asking figure 2A show RF beamforming receiver architecture, and figure 2B show LO beamforming receiver architecture. Considering these architectures, which of the following statement are true and which are false? So the pictures is here, but we're gonna go back to the questions. So in the LO beamforming receiver, the phase shifter can be replaced by a true time delay for wideband operations. So this one is false, because like for like true time delays, the operation is narrowband, it's not wideband. And for B, the phase shifter design is typically more challenging than RF beamforming receiver compared to LO beamforming receiver. And so I think if you go over the one of the lecture note professor posted about architecture design, then in there it said the LO beamforming receiver is easier to design compared to RF beamforming receiver. And the main reason is the phase shifter in the RF has like higher loss, and so it can attenuate the signal more compared to the situation in LO beamforming receiver. And so LO beamforming receiver is like less challenging compared to RF beamforming receiver. The LO beam for problem C, the LO beamforming receiver can support multiple simultaneous beams, while RF beamforming receiver cannot. So this one is false. And so I think both of these configuration can only support like one beam at a time, and so this one is false. There's no difference between the mechanism of the two, so this one is false. The mixer, for probably the mixer in LO beamforming receiver do not need to handle as many blockers as a mixer in RF beamforming receiver. So this one, I'm not sure what like blocker means, but in the solution it said false. So we can let's leave it as false. Problem E, LO distribution is more challenging in LO beamforming receiver as compared to RF beamforming receiver. And so this one is true. And so if you remember the picture from, let's say, from the LO beamforming, and you can see like the LO, so it, first of all, you need to route like too many elements. So it's not only 2, it can be like 16 elements. And so like the LO have to route to all 16 elements, and it need to be on the correct phase and correct amplitude. And normally like is more challenging to route like this LO path. And the last questions, the LO beamforming architecture is commonly used in multi-IC scale phase array. And the solution is false. And I think the solution is false because like in multi-IC scale phase array, like we have to, like if we do beamforming with like a lot of IC, then we have to route the LO into different IC on the PCB, for example. And yeah, like routing LO on like to have the correct phase and correct amplitude to every element is challenging. So this one is not commonly used. Okay. So okay, so 6 questions. A sliding IF receiver used to step down conversion in figure 3 using PLL, frequency multiplier, and frequency divider. The receiver cover 2 channel, blah blah blah, that have the frequency of this one and this one. What are the corresponding output frequency of the PLL to support these channels? What are the corresponding image frequency of in each case? So problem 6 refer to this figure, and so if we look at the receiver path, we can see that we have 2 mixers. The first one, let's say we have like frequency at the input of the LNA, and then we have frequency IF, and then that IF is again down converted at the baseband, which is 0. And for the PLL, we have like 2 F PLL here, and then we have F PLL divided by half here. And so we have so in order to down convert the signal to the IF frequency, we can either have this case. So let's say we have FIF here, and we have signal frequency here. And so we can either have 2 scenario where we have the 2F PLL is below the F frequency, 2F PLL, and the difference between these two is IF frequency. So that is one scenario, and the second scenario is the 2F PLL is above the signal frequency. So we can have signal frequency, and we can have 2F PLL here. And the difference between these 2 frequencies is again IF. So depending on which mode of which of depending on the configuration we choose, then we can have two different answers for PLF frequencies. And also like the problem also asks you to find the image frequency. And so in the first case, the image frequency is gonna be in here. Also, it's not here. To this erase. So it's gonna be symmetric across two FPLL. So I have, and in the second case, the image frequency is going to be above PLL frequency. So FIF, and this one is F image. So yeah, depending on which mode of operation you choose, then you have two different sets of answer for PLL frequency and image frequencies. So I think that is for problem 6. Yeah. Okay. So for problem 7, then derive quality factor Q total for a series resonance circuit with inductors and with inductor with quality factor of QL and a capacitor with quality factor of QC. And so series resonance circuit. So you would have you have inductors and you have capacitors. And one over J omega C for capacitor and RC capacitor. Okay. And so you can check. So we can have like the quality factor of the capacitor is 1 over omega C RC, and quality factor of inductor is omega L divided by RL. And so the Q factor of the resonance systems is gonna be defined as the just check very quickly. I need to close my window. So the Q factor of the resonance system is gonna define as omega naught multiplied by the energy of the magnetic plus the energy of electrics divided by dissipating power. Okay, and so that gonna be equal to Q gonna be equal to omega naught multiplied by so the energy of the electromagnetic is the energy of the inductors, and the energy of the electric is the energy of the capacitor, and then divided by the energy across RL and energy across RC. Sorry, power across RL and power across RC. And so because of the resonance, you have because of the resonance, you have the energy of inductors equal to energy of capacitor. And so you have Q total equal to 2 omega naught of EL divided by PRL plus 2 omega naught of EC divided by PRC. Okay, and so this term is 1 over QL, and this term is 1 over QC. Wait. I think I made a mistake here. Okay, so Q total. Yes, I think I made a mistake here. Let me just correct this very quickly. So from these equations, what we have is 1 over Q total equal to P of RL divided by so we have like EL equal to EC, and so this one equal to 2 omega naught EL. And so we have PRL divided by 2 omega naught EL plus PRC divided by 2 omega naught EC. Okay, and so you can find out that this term equal to 1 over QC, and this term equal to 1 over QL. And so we have 1 over Q total equal to 1 over QC plus 1 over QL. Okay, so that is problem 7. And so for problem 8, so this one is about the VCO. VCO used a combination of fixed inductors and a binary weighted switch capacitor and varactors for frequency tuning. The smallest switch capacitor achieved a minimum capacitance of C min SC and a maximum capacitance of C max SC. The minimum and maximum capacitance of the other switch capacitor scale linearly in a binary manner, so to C min to C max, etc. The varactor achieves a minimum capacitance of C min var and maximum capacitance of C max var. What should the relationship between C min SC, C max SC, C min var, and C max var to ensure there's no frequency hole in VC frequency tuning curve? Okay, so for the varactor problem, for this problem, first of all, you have to see like what is happening. So we have 2 mechanisms to tune the frequency. We have the binary weighted switch capacitor, and then we have varactor. And so if we use a binary weighted switch capacitor to tune the frequency, then what we're going to achieve is a very discrete frequency selections. And the distance between the frequency is Y. So we use binary weighted switch capacitor for our cost tuning, meaning that we're gonna use it to tune a very wide frequency. For varactor cap, it's like very continuous frequency tuning, and so we use a varactor for fine tuning. So normally we use a switch cap to select sort of like the region we want to set the frequency to, and then we use a varactor to like sort of tune to the correct frequency we want to set to. And so if we look at it this way, then you can see that like the frequency like the switch cap gonna have like discrete frequency selections, and so it's gonna have like a finite difference between the frequency selections, and so the continuous the varactor have to be like wide enough so that it can cover the range of difference between these two discrete frequencies, and so that is why in the solutions. So that is why in the solutions, we can see that the inequality to govern this condition is we have Cmax switch cap minus Cmin switch cap. So this one is proportional to the discrete frequency difference. And this one must be less than maximum varactor capacitance minus minimum varactor capacitance. And so this is the idea for problem 8. And, okay. So that is for problem 8. And for problem 9, a phase array antenna has four antenna elements with an antenna spacing of lambda over 2. Each antenna element is isotropic and radiates PTX power. And so the part A asking what is the effective isotropic radiated power in the broadside directions. And so if you look at the equation of effective isotropic radiated power, you can see that we have like 4 elements in the system, and so the effective isotropic is it's going to be 16. The transmitting power in a single element. Okay, and then for part B, you can use the equation, the array factor equations, and you have to set the observation angle to be 60 degree, and that one gonna lead you to 0. And then you do the same for C and D. And so these problems are only apply equations, so I'm not really going depth into this. Okay. So for part 10, for problem 10, let's see how many we have left. Hmm, 11, 12. Wait, not too bad. Okay, so for problem 10, so this the mechanism of the this phase shifter, you can take a look. You can see the intuitions in one of the lecture professor posted on coursework. But like the idea for adding an inductors here. So basically they have like vector C1 and C2, especially for C2. So in C2 they add the inductor L1, and the reason why they add the inductor L1 is that the tuning range of C2, the effective capacitance, if looking at into L1 gonna be like wider than C2. And so okay, let's say if we set the C2 to C2 mean, and then so if we look at the into L1, what we're gonna see is some sort of capacitance, and we call that capacitance C effective mean. And so we have 1 over J omega C effective mean. Yeah.
Should we get like the plus guide to look at the
Give me 1 second. So I'm doing some work now. I'm gonna be done at 3:30.
Do you think we should ask them to look into it?
Yeah, that's fine.
Yeah.
Okay. So so looking into like L1, we're gonna see some capacitance impedance. And so if we call this C effective mean, and so what we have is 1 over J omega C effective mean gonna be equal to J omega L1 plus 1 over J omega C2 mean. Okay, and if we set the C2 to like C2 max, then we have also had another equation for 1 over J omega C effective max. And so and then you get the ratio of these two, C effective max divided by C effective min. And so that will lead you to this equation. Okay. So that is for problem 10. See for problem 11. So as shown in figure 5, a phase array has been built using 2 transmitter chips, each having 4 elements. Each transmitter has a single analog input and baseband up. Baseband up converts the input to millimeter wave frequency, split the result signal into 4 paths, independently phase shift and each path, and amplify the signal on each path to drive respective antennas. The chip outputs are connected to 8 linear and isotropic antennas spaced lambda over 2 apart. Unfortunately, the chips were fabricated and the designer found that the on-chip phase control doesn't work, and all the phase shifter are always stuck at the same phase shift value. To solve the problem, they decide to attach one phase shifter to each chip on the board level. So for part A, it's asking us to fill out the gap. So for part A, when off-chip phase shifter have a phase shift of 0 degree, the resulting antenna pattern on the far field will resemble the array factor. So in this case, like we have no phase difference between all elements. So that means we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 elements. Linear array with lambda over 2, antenna spacing, and 0 degree phase shift between elements. And so for that is part A. For part B, when the off-chip phase shifter have a phase difference of 120 degree, the resulting antenna pattern in the far field will resemble the product of the array factor of. So let's see. So in this case, we have like 0 degree here, and we have 120 degree here, and so we can see like these are like clearly like forming two beam forming pattern. So the first one gonna be like directly, and the second one it can be like off a bit, and so the combination of these two beams gonna be equals to if we have like two elements with like a phase shift of 120 degree apart, and the distance is lambda. Let's see, lambda, actually 2 lambda, and the reason why it is 2 lambda is that that is the corresponding distance. So the distance between corresponding antenna elements. So the first antenna element of chip 1 is going to be here, and the first antenna element of chip 2 is going to be here. And so 2 lambda is going to be the difference between these two. So so that is for the first part, and so we're going to have like two main beam, and in each beam we have 4 elements, and each element is going to be like phase shift different 0 degree, and the distance is lambda over 2. Let's see, so I'm just filling the gap here. The products of array factor of 2 elements with linear array with 2 lambda spacings and 120 degree phase shift between elements, and array factor of 4 elements with lambda over 2 spacings and 0 degree phase shift. Okay. So that is problem 11. And then for problem 12, okay, so we have the two figures, the F max versus current density figure, and we have a common source transistor figure. And so it asking the first problem, the part A asking what is F max with respect to current density for single transistor, and then what is the maximum gain at 60 gigahertz. And so if we look at this figure, we can see that like at this current density, like F max is the maximum, so we want to choose this this point. And so if you plot let's say maximum gain G max versus frequency, you're gonna see something like this, and this one is F max. And so at the F max you have G max of 0 dB, meaning that like the transistor doesn't produce any gain. And so if you want to find G max at let's say F1, if you want to find G1 at this point, then you have to know that the slope of this line is 20 dB per decade. And so you have to find how many decades between F max and F1, and then you multiply by 20. And so the equation is 20 times log of F max over F1. Okay, and so in this case we have F max of let's say 160, maybe 170 or something. 170, and then F1 is 60 gigahertz, and so the gain at 60 gigahertz is gonna be 20 log of 170 divided by 60, which is so around 9 dB. Okay, so that is for part A. So for part B, so the transistor has a DC to AC efficiency defined as a IAC over IDC square equal to 0.2. And IDC is a DC current, and IAC the amplitude of the sinusoidal current at 60 gigahertz. The output impedance at 60 gigahertz is 200 ohms, and at DC 2 ohms. And we have to find IAC and IDC in order to generate 0 dBm power at 60 gigahertz. And so we also use the optimum current density obtained from problem 12 to calculate the size of the transistor. So for this problem, we have to find the current, the AC current first, because that is simple to find. So if we want to find the AC power, then it's gonna be equal to 1/2 of IAC square multiplied by RAC. And so we have RAC equal to 200, and PAC is 0 dBm, which is 1 milliwatt. And so from that we can find IAC. And let's see. So from solutions, it said IAC is 3.1 milliamps. Okay, and then from that you can find IDC, because there's efficiency equations, and you can find IDC equal to 6.93 milliamps. And so if you know like IDC, and you use this graph to find the current densities, and so you can see the unit of current density is milliamp per micrometer, and micrometer is the width of the transistor. And so if you want to find the width of transistor, then you just need to get the current you divided by the current densities. And so that will give you the width, which is 35 micron. So that is part B. And then part C is Fmax is a function of gate resistance, which depend on transistor configurations. Maybe I need to scroll down a bit. Okay, so this figure, let's see. So figure 7 show different transistor configurations for a given total width W, assuming the gate resistance solely depend on poly resistance. Quantify how Fmax change with B, C, D compared to A. And okay, so in here, so first of all, we have to find, well, we know that the resistance equation is going to be R multiplied equal to rho multiplied by the length divided by the area. And so the resistance we care about in here is, let's see what it say. Depend. So it said Fmax is a function of gate resistance. Okay, so in here we have to find a gate resistance, and in this case the gate resistance is going to be defined as this resistance RG. And let's see, in the second case it's going to be these two resistance in parallel. And in this case, like these 4 resistance. And the last one is we have like doubly contacted transistor, meaning that both ends of the resistor are going to be connected to each other. And so if you use these equations and you look at these figures, and then you can find like B is like have lower resistance than A, and C has lower resistance than C. Then C has lower resistance than B, and D has lower resistance than C. And see. So I'm not sure why the relationship. So according to the solutions, B is let's see, B is like 2x times better than A, and C is 4x times better than A, and D is 8x times better. So let's see, why is it like that? So if we have RG here, in this case we have RG1 here, and we have RG1 by half here. And then in this case, we have each resistance going to be G1 divided by 4, because the length is divided by 4. And then
the area is all the same, right?
the area the same, but
Okay.
I mean like this length is like divided by half.
Mm-hmm.
And so I think if you capture this resistance, then that tells you like how much at max is improved. Okay, and so in the last case, you have doubly contacted. It means like these 2 ends are connected with like way better resistance. So normally we have PC for polysilicon's or for gate like for gate resistance, but on top of that you have for example, if you see in the homework problem, we have like M1, and we also have M2 metal on top of that. And so these 2 metal have like better resistivity compared to PC. And so it has like better contact compared to PC. And so if you like sort of like imagine this like M1, M2, for example, like short the connection between two ends of the PC, then this considered short. And so in this case, you have like the gate resistance is even divided by half in here. So this one is G1 divided by 8. So I think that is the rationale. Okay, so that is the end of the midterm. Maybe I can quickly go over problem. I think there's a homework problems See that he already, I think Professor already posted the solutions. Let me just check. So for homework 1, okay, so homework 1 is phase array. Okay. And homework 2, let's see. Homework 2. Okay, so it's about Wilkinson divider. Yeah, so for this problem, if so in here he sort of use he calculate the SNR in terms of powers using like limitation functions, but you can also use the S parameter to to solve this problem. And yeah, so S parameters also give you same answer. Let's see. So that is homework 2. Homework 3. Homework 3 is all about simulation, so that's fine. Homework 4. Okay, we haven't got to homework 4 yet. Yeah, so if you study the midterm and homework 1 and homework 2, then I think you're pretty set for the midterm. Yeah. You have any questions?
That sounds good.
Okay. Yeah, so if you like when you study for the midterm and if you have any problem, just let me know.
Yeah, sure.
Yeah.
Sounds good. Tomorrow is at 5 to 7:30.
Yeah, it's 5 to 7:30. I think
Okay.
the solution gonna be sorry, the midterm gonna be like 2.5 hours long.
Okay. And then for homework 4, which I just saw, is there like layout or no? Just calculation.
Maybe I can share the screen a bit. Okay, so this one. So this one is not a layout problem.
Yeah, since just have calculations.
Yeah, so the problem one is like theoretical problem.
Yeah, looks good.
Yeah. Oh wait. Oh yeah, these are like very good questions. Like it help you understand more about like design in general. They are very good questions. Yeah.
Nice. Okay, cool. Thanks.
Okay, so I think I'm gonna stop the recording now. Stop.